All right, this is lecture 28 on section 11.9, representations as functions as power series. So I just want you to think for a second, remember back to some of our geometric series. So keep in mind, if we have this series 1 plus 2/3 plus 4/9 plus 8 over 27 plus 16 over 81, one way that we can represent this is the series from n equals 0 to infinity. So we're going to start them at 0 this time. And if you notice, on the top of the fraction, we have powers of 2. So that's 2 to the n. And on the bottom, we have 3 to the n. And really, this is the sum, n equals 0 to infinity, of 2/3 to the n. Now we know that this converges because our r is 2/3. And when it's written starting at 0, so now we're used to it written as n equals 1. So keep in mind that when we're written from n equals 1 to infinity, we want a times r to the n minus 1. And so that way it starts, when you plug in the 1, it starts at 0. This is equivalent to saying we want this series to start at 0 and have a times r to the n. So in this particular situation, remember that this will always converge to a over 1 minus r. So for in this case, this series is equal to, our a in this case is 1 because I'm not multiplying my 2/3 times anything. So this is 1 over 1 minus 2/3, which is 1 over 1/3, or just 3. Okay. So the same idea we want to apply to the power series. So if we look at the power series when we have n equals 0 to infinity of x to the n, this converges and is equal to, so we will have the sum n equals 0 to infinity of x to the n is equal to a over 1 minus r. So our a in this case is 1, and our r is the x. So 1 over 1 minus x. So what we end up with is a function on the right, 1 over 1 minus x, is equal to a series on the left, a power series. And so we can actually use this, and you'll notice that I have this written again down here. So this is your reference point. We know that our traditional power series of x to the n is equal to 1 over 1 minus x. And so the idea is, can we use this information to write different functions as a power series? So how can we adjust this to write other series? Well, let's take a look at a few. So we are trying to go from 1 over 1 minus x, because I know that series, to this one right here. Okay, 1 over 1 minus x squared. So in order to go from here to here, all I'm doing is I'm making my x and turning it into an x squared. So that means that the series that I want here, so 1 over 1 minus x squared, is going to be equal to the sum n equals 0 to infinity. And instead of having x to the n, I'm going to replace the x with an x squared. So I'm going to have an x squared to the n, which is n equals 0 to infinity of x to the 2n. So that's a series, and if we write out the first few terms, if you plug in 0, that's still 1. If you plug in 1, now you get x squared. If you plug in 2, you get x to the 4th. And so what happens is you're getting even powers only. Okay, so that's what happens when I square things, right? So that's how we would get that one. Okay, so the idea is, how can we adjust the series that we have, knowing that 1 over 1 minus x is equal to x to the n? Okay, so I need to go from 1 over 1 minus x to 1 over 1 plus 4x cubed. Okay, well, notice that I have a 4x cubed in the negative x spot. So my x has to go to be negative 4x cubed. Okay, so that's what I'm going to sub in. I'm going to sub in this for my x in the series. So my new series, so this is going to be equal to the sum n equals 0 to infinity. And my x is now going to be negative 4x cubed to the n. And so what happens here is we get, if I separate this out, which you don't have to, it's totally fine that way, negative 1 to the n, so it's alternating, times 4 to the n times x to the 3n. So your powers are multiples of 3 now. And if you plug in the first few, you plug in 0, you will get 1. right? Plug in 1, and you get, this actually becomes minus. We can fix that. And that's going to be 4x cubed. And then the next term, when I plug in 2, it's, whoa, sorry about that, friends. That jumped on me real quick. All right, so we are back here. So we are adding the next term, and that is going to be 16 and x to the 6th. And one more term, minus 64 x to the 9th, so on and so forth. Okay, so we can write out the series that way. Okay, now this one's a little bit trickier. So first of all, I'm going from 1 minus x. So the first thing I have to do is go from 1 minus x to x plus 2. Okay, well, how can I do that? Well, if I make the x negative, so if I'm starting here and I make the x negative, that gives me 1 plus x. So this means that goes from my x to negative x. And then I've got to put another added 1 in there. So let's see what happens if we were to make your x become negative x plus 1. Does that work? So if I plug that in to here, I might want minus 1. Let's see. Then I'm going to get 1 minus negative x plus 1. I think I do want minus 1. See how we're just kind of fitting it, making it work? How do I substitute in there? Let's see. That does gives me 1 plus x plus 1, which is x plus 2. So that's what I want, okay? So what I want to do is I want to make my x negative x minus 1. Okay, that'll get me this bottom piece. Okay, but then I have to multiply by x cubed once I get it. So that means that I have the following. I have that 1 over x plus 2 is going to be the series n equals 0 to infinity of, I'm replacing the x with negative x minus 1 to the n. Then, in order to get the x cubed on top, to get x cubed over x plus 2, I'm just going to multiply it by x cubed. So I'm going to take this one, n equals 0 to infinity, and I'm going to take x cubed and multiply it by negative x minus 1 to the n. And I'm going to leave it just like that, right? And we can take a look at the first few terms, but I'm going to skip it for now. Okay. Yeah, let's go back and do it. Okay. First couple terms, if I let n equal 0, then we get x cubed times negative x minus 1. So this is x cubed times, that's it, just x cubed, right? Because anything to the 0 power is 1. Then you're going to have x cubed times negative x minus 1. And so that gives you x cubed minus x to the 4th minus x cubed, right? So notice what happens. The x cubes actually cancel out there. And you're left with just negative x to the 4th. And then if you take on and add an additional term, so this is, actually I'm going to not rewrite that. We'll just keep going here. We're going to add on some additional terms. So your next term, when n is squared, you're going to have x cubed times negative x minus 1 squared. Okay, and I'm not going to write that one out. But you can see the terms are a little bit harder to write out, but you can still do it. And that's the series that you have. Okay, so now we've been able to rewrite some of these that involve just some algebra, maybe plugging in for a different value for x, or multiplying, maybe dividing, whatever you need, okay? However, you can also do something really cool, which is you can also take derivatives and integrals of series. Okay, if you just think about integrating the x to the n or differentiating the x to the n, you can do just that. And so we have a theorem that tells us we're allowed to do that. So here's what you got. So if the power series Cn times x minus a to the n has a radius of convergence r, which is greater than 0, right? Then the function f defined by f of x equals, oh, sorry, there's a typo. This should be C0 plus C1 x minus a plus C2 x minus a. And that's the case down here as well. This should be C sub 1. Is differentiable and therefore continuous on the interval of convergence, or the radius of, the interval of convergence. Okay, so here's how we do it. So when you take the derivative of your series, right, when you think about it, you've got C1, C naught plus C1x minus a plus C2 x minus a squared. And if you think about taking the derivative of that, the derivative of the C naught term is just 0, so it goes away. The derivative of the x term is just the C1, the number in front. The derivative of C2 x minus a squared, you'd be multiplying by 2. So 2 times C2 times x minus a. Decrease your exponent by 1. Same kind of thing all across the board. In general, what you're doing is you're, from here, bringing down this n, multiplying by the n, and decreasing your n by 1. Okay? If you're trying to integrate it, you're going to do the opposite, right? You're going to add 1 to your exponent, divide by your new exponent, and you're going to add an arbitrary constant. Okay, so exactly the same thing. All right. So let's see how that's going to work. Okay, so in order to get the function 1 over 1 minus x quantity squared, we recognize that this is related to the derivative. So if I think about having f of x equals 1 over 1 minus x, and I take the derivative of that. Now, hold on, let me change my function notations here. Let's make it g of x. Let g of x equal this one. Then g prime of x is, let's see, this is 1 minus x to the negative 1. So if I take to the derivative, that's negative 1 over 1 minus x. Decrease your exponent by 1, so it becomes squared on the bottom, times the derivative of the inside, which is negative 1. And those negatives canceled. So this actually turns out to be exactly what we want. So the function we want, which is this one here, is the derivative of the function that we know. So if we do the same thing to our series, so our series here for this one is n equals 0 to infinity of x to the n. And what I want is its derivative. So I can take the derivative. Now, the first term is a 1, so when you take its derivative, it goes away. So now instead of counting from n equals 0, I've got to count from n equals 1. And then I take the derivative, so bring down my n, decrease my power by 1. So this is my series. You want to write out the first couple terms. Sorry, we're jumping around again. If you want to write out the first few terms, when you plug in 1, you get 1, right? 1 times x to the 0 is 1. When you plug in 2, you get 2 times x. When you plug in 3, you get 3 times x squared, so on and so forth. Okay, which makes sense. Number 2, how do we get an ln situation going on? So if I think about starting with g of x being my 1 over 1 minus x, then natural log is related to the integral of this. So if I think about this as 1 minus x, if I think about what is the integral of g of x dx, then this is a baby u sub, so little u is going to be 1 minus x, and du is negative dx. So that means this is the same as the integral of 1 over u times negative du. Antiderivative here is natural log of u with a negative. And so our final answer here is going to be, let's see, negative natural log of 1 minus x, which is close to what we have, okay? We have the opposite of that. So what we need to do is we need to take the integral, but we need to take the negative integral, okay? So the negative integral will get me my function, okay? Okay, so then if we think about starting with the series for g of x, the series is n equals 0 to infinity. of x to the n. And so what we're going to do, by the way, there's always a plus c here. Okay, so then we want the negative integral of g of x dx, and that's going to be negative, so sum n equals 0 to infinity, negative, and then the antiderivative of this is going to be x to the n plus 1 over n plus 1 plus a constant. Okay, and so this is what's equal to the natural log of 1 minus x. So notice that you can use derivatives and integrals to build your functions. How about arctan of x? Well, arctan of x looks kind of like 1 over 1 minus x if I look at its derivative. So if I think of g of x as 1 over 1 minus x, well, I really need this to be 1 plus x squared. So let's let x become negative x squared. Okay, if I do that, then my g of x is now 1 over 1 plus x squared, and the integral of g of x dx is the arctan of x, which is what I have. Okay, so now if I start and do the same procedure with my series, I'll get my answer. So this one is n equals 0 to infinity of x to the n. And the first thing I want to do is this. I want to change my x to negative x squared. So I'm going to make this n equals 0 to infinity and a negative x squared to the n. And this is the same as the series n equals 0 to infinity, negative 1 to the n, x to the 2n. Right? Okay. Now we want the integral of that. So the integral of that is going to be the negative 1 to the n doesn't change anything. That's just a coefficient in front, so I'm going to let that go. And then I'm going to take the antiderivative of my x to the 2n. So I'm going to make it x to the 2n plus 1 all over that new exponent, which is 2n plus 1. And that represents the arctangent of x. So essentially, we want to think about if I start at my original function 1 over 1 minus x, how do I arrive at the function I'm being asked to represent? Then we apply the same procedure to our series, and that will give us the series for the function in question. Okay. All right. It appears as though that is the end of my notes.